to try to wrap up some things here with Newton's second law of motion that wasn't on the last segment, what we want to do is, now that we've had some time to work some of these problems, let's kind of go back and make sure that things make some sense. So if I take a look at an equal force being applied to both of these sets, okay? If you look at the force here, and I look at the force here, it is the same. But notice that if I apply that force to one cart, the full length of my acceleration here, okay? That's a very large magnitude. Whereas if I apply the same force to the set of multiple carts, my acceleration is much, much smaller. That is because, remember, if I'm pushing on the single cart versus the multiple carts, the acceleration is smaller because the multiple carts have more mass. So the larger the mass with an equal force, the smaller the acceleration. So if I push on the single cart, I get an unbalanced force. If I push the chain of 8, the acceleration still happens, but it is much less because there's more mass. So let's think about this and extrapolate it a little bit. How would the acceleration of a chain of 2 carts compare? Okay. The two cart chain would accelerate at half of the rate. Okay, so it would be half of the acceleration because it has twice the mass. This is what we call an inverse relationship. Now, Newton's second law also allows us to talk about weight and mass. Weight and mass are different. Okay, weight is very different from mass. And this is because we tend to use it kind of interchangeably, but they are different. And we kind of mentioned this when we were talking about measurements. Weight is different in different parts of the universe. Mass is not. That's because weight is a force that the mass produces due to gravity. Because gravity is different places in different parts of the universe, your weight will change, but your mass will not. The weight formula is actually a hybrid of the force formula. So if you understand the idea of force, you really don't have to memorize a whole separate formula here. My weight is a force and is equal to the mass times the acceleration. But remember, here on Earth, we know what that acceleration is. Okay, we're representing it here for g, and that is 9.8 meters per second squared. All right, so basically if we know our mass and we know the acceleration due to gravity, we can actually find our weight because weight is a force. All right, so we have this comparison here. An astronaut on Earth, his mass is 88 kilograms, and on Earth, his weight is 863 newtons. All we did was take the 88 times 9.8, and that's what we get. But on the moon, the acceleration of gravity is a lot less than here on Earth. So while his mass stays the same at 88 kilograms, his weight does not. It changes to 141 newtons. Okay, so this also brings into account this idea of friction as it applies to Newton's second law. Friction is a force that opposes the motion of objects that touch as they move past each other. This is what you actually feel as a result of rubbing, let's say, your hands together. You feel that heat. That heat is actually a result of the friction. Friction is what allows us to do things like pick up a pen or a pencil and hold things in our hand. Without friction, none of that would be possible. Friction acts on the surface where objects are in contact. And what this does is it decreases the amount of force. So if I'm pushing something with a certain force, its net force will be reduced because there's going to be some friction involved. Now this also leads us to the concept of gravity. Gravity is a force that acts between two masses. It is an attractive force, and what it does is it pulls objects together. Now we know Earth's gravity, and we've talked about it several times already in this unit. It's 9.8 meters per second squared, that's its acceleration rate. but the direction that it pulls is downwards towards the center of the Earth. So gravity with this boulder is actually pushing it downwards, but it is balanced. This is a balanced set of forces that is counteracted by the supporting force of the rock underneath it. If that didn't occur, if that underneath supporting force wouldn't happen, then the rock would actually fall and be accelerating. And we already talked about how to solve those free fall problems. Okay, gravity causes objects to accelerate downward. How fast they are accelerating in general, now this doesn't hold on Earth, but we're talking in the universe, how fast objects accelerate towards each other are going to depend on the mass of the object and the distance between them. As the force increases, you've got two choices. You either have to get the mass increasing or the distance increasing. Okay, so here we've got this flying squirrel, and he's got gravity pulling him down, but the air resistance is pushing him back up. Gravity is a constant force. It doesn't change. It can't be affected by temperature. It can't be affected by different chemicals that are present. Each individual object has its own unique gravity, and that does not change. It's what actually gives the universe its shape. All objects within the universe fall with the same acceleration due to gravity, no matter the mass. So in other words, if you're within the influence of something, let's say like Earth, okay, all of the objects on Earth should fall at the exact same rate, same acceleration. Now that's not to say that they aren't affected by air resistance differently. That's a different force, that's an opposing force. But if we take air resistance out, objects within the influence of Earth's gravity should fall at that rate of 9.8 meters per second squared. So in order to show that, that's the case, you actually usually have to use a vacuum tube where you've had all the air sucked out of it. If you have a feather and a ball and you have them in the vacuum tube, they will fall at the same rate. The reason why, if you do that, let's say off of the second story here out of a window, and that doesn't happen, is because there's air resistance. So the feather obviously is much more influenced by the air resistance than the ball, and they will appear to fall at different rates, when that is actually really not the case.